Hello again. Uh, Welcome to Forecast Evaluation chapter. In the previous chapters, we talked about forecasting in overall and some forecasting methods. In this chapter, we will be focusing on how to evaluate if the selected forecasting method is working. In revenue management, we first do forecast for a given period, then we set controls to maximize our revenue and profit. We also have to monitor if our forecast is right. Look at this basic graph, right? If black line is actually happened, but you forecasted the red line, this will be a big failure for your method, and most likely you will not able to optimize your revenue. So you're going to have a scheduling and service problem. Let's say this is a restaurant. Considering your forecast was lower than actual, you didn't even order necessary resources like food ingredients to serve the people, right? So because you relied on faulty forecasting, basically you failed to do your job. Um, the question is then, how do we evaluate your forecast, right? That's the basic fact. In order to evaluate the different forecast methods, um, we need to understand several factors, such as assumptions related to method selected, criteria used for various techniques employed, and also we will talk about how to measure error between forecasted value and actual results. Now, let's not forget the evaluating forecast method is multidimensional. It includes the underlying assumptions, you have to understand them well, and testing the accuracy through various error measures, and conducting, if possible, out of sample testing. This comprehensive approach ensures we are not just blindly trusting our methods, but understanding and improving them if needed. So you're not just going to do something and you accept that the outcome is perfect, so I don't have to do anything about it. You always need to work, because let's not forget, even if your method's working at the time, because the things change over time, your property structure, maybe people around, maybe events, there is a lot of things changing. So you should continue to improve and be sure that the methods you select is working. Now, every forecast is built on a set of assumptions. And I just want to clarify that different methods might require different assumptions. But overall, the assumptions that there exists an identifiable pattern, right? There's not some random things, like you can identify some pattern going on there within the forecasting model. It suggests that historical data exhibits a behavior or trend that can be detected and expected to continue in the future. When you look at the graph charts, you can say, you know what, I can see something like some trends or some kind of movements that you can identify. Um, Basic example in the picture showing a repeated pattern, like say weekly hotel occupancy, increase in weekends and decrease in the weekdays. The model then uses this pattern to predict future outcomes. But it is not enough to just find a pattern, right? We must also trust in its stability. So, which means the pattern we got from historical data must hold true for future periods. This is what gives our forecast their backbone. For instance, if a retail company analyzes its sales data over several years and finds that sales consistently increase in November and December due to holiday season, this is an identifiable pattern. A forecasting model could then use this historical pattern to predict higher sales in these months for the upcoming year. This pattern doesn't have to be a simple trend. It could be also like a cyclical pattern, like the ebb and flow of tourist numbers throughout the seasons and in a resort town, for example. Or even a more complex pattern, like the fluctuation of stock prices influenced by the certain economic indicators. The key to using these assumptions effectively is to have enough historical data to confirm that the pattern is persistent and not just a random occurrence, right? It's not randomly came about. So once a pattern is identified, it can be quantified and included in the forecasting model to improve its predictive power. Now, let's consider the core yardstick we use to evaluate our forecasting method, right? So these criteria are not just a checklist, they are the rigorous standards our forecast must meet. So you have to understand them. We start with the structure. Is the model well architected? Is it logic sound and reflective of real world? Like, this is crucial for reliability. Then we ask if our model is specified. It is transparent, not a black box. So we need to see and understand the gears that turn to make our predictions. You need to understand ins and outs of the methods you are using. That's why we talk basics of some of the methods like moving average, how it works, etc. So the plausibility of our results comes next. Do the forecasts make sense in the context of what we know about our market and environment? They should align with our business approach, right? Business understanding. Parsimony is about simplicity, stripping away the unnecessary to leave a model that is lean and efficient without sacrificing insight. You want as simple as possible, so you can understand what's going on there. So we also look for, of course, explanatory power, right? Our model should illuminate the why behind our forecast, offering understanding alongside the numbers. Robustness is also about strength. Our model must stand firm in the face of outliers and not be too sensitive to extremes, or you should at least make it robust. We weigh the cost of development, data gathering, and maintenance against the benefits, always with an eye on the bottom line. And acceptability, of course, the model must be understandable and inspire confidence for those who rely on its predictions. It must pass the test of practical confidence, not just statistical significance. Basically, when you look at it, it should make sense. I'm confident in what I'm doing. I accept it. Of course, the accuracy, perhaps the most straightforward criteria, that this refers to model's ability to produce forecasts that closely match the actual outcomes. Accuracy is often primary focus when evaluating a forecasting model's performance, right? That's what we are going to do when we find the errors. And each of these criteria contributes to overall assessment of whether this forecasting model you select is a fit for our purpose. So they help ensure that model not only predicts the future accurately, but also does so in a way that is understandable, reasonable, and cost effective. Now, when we talk about accuracy in forecasting, we are essentially talking about how closely our predictions align with reality, right? So you made an assumption, and you did some forecasting, and the real result came, and you look at if your forecasting is aligned, is similar, right? So the key measure here is the forecast error, the difference between what we forecasted and what actually happened. So it is a straightforward concept, but it holds immense weight in evaluating our methods. Now, we observe errors over a period, and these errors tells us not just about the magnitude of our misses, but also about the direction, whether we are consistently overestimating or underestimating. Understanding and minimizing these errors is pivotal to enhancing accuracy of our forecast. After all, in the world of forecasting, accuracy isn't just a metric; it's a goal, right? So that goal is basically I want to be as accurate as possible. Now, let's start. Errors, like I said, between difference between forecast and actual value, right? So let's start with the mean error. And importantly, it is limitation in the realm of forecasting. While a mean error calculates the average of forecast errors, it has a critical drawback. It can be misleading due to its methods of calculation. The issue arises when we consider how mean error handles positive and negative errors. Imagine our forecasts sometimes overestimate, sometimes underestimate the actual figures. In such cases, positive and negative errors can cancel each other out, leading to a deceptively low mean error. This gives a false sense of accuracy. For instance, if all our overestimations are just as frequent as our underestimations, the mean error might hover around zero, like the example here, right? So this suggests that non-existent accuracy, but we know there is a problem, the issue. So therefore, while mean error can give a quick snapshot of forecast performance, it can be quite deceptive. It masks the true extent of forecasting errors, failing to provide a clear picture of the model's accuracy. This is why in practice we often prefer other measures that accounts for this limitation, which we're going to talk in a minute. After discussing the limitations of mean error, we turn to a more reliable measure, what we call the mean absolute error, or MAE. Unlike MAE addresses the issue of error direction by considering the absolute value of errors. This means both overestimation and underestimation are treated equally, providing a more accurate picture of forecast accuracy. MAE is calculated by taking the average of these absolute errors. It's straightforward yet powerful. For instance, if our forecast, just give me a second, sorry, let me close this. For example, if our forecast errors, which is the example you can see on the slide, in 4 consecutive periods, which we calculated previously in the mean error, MAE calculates the average without letting positive and negative values cancel each other out. The result is clearer, more honest assessment of our forecasting model's performance. In essence, MAE offers us a lens that focuses solely on the magnitude of errors, like undistorted by their direction. It is an essential tool in our forecasting toolkit, especially when we need to understand the typical error size our model is likely to produce. Building on our understanding of error measures, let's focus on the mean absolute percentage error, or MAPE. MAPE steps beyond mere absolute error values. It expresses errors as percentage of the actual values. This relative measure helps us understand the size of the error in the context. MAPE is particularly useful when comparing forecasts across different scales or units. For instance, if we are comparing sales forecast of items with vastly different volumes, like think about it. You are looking at the revenue, tens of thousands of dollars. If you use the MAE or even ME or MAE, that value is going to be huge. Like because of tens of thousands of dollars, even the small variation is going to look like hundreds of dollars. But in the other hand, if you are looking at comparing it to, let's say, occupancy is up to 100%. So even if like in $10,000, 5% difference is 500, right? But in the 100% occupancy, 5% is 5%. So to calculate MAPE, we take the absolute error, divide it by the actual value, and then express it as a percentage. This provides a clear, intuitive measure for forecast accuracy that is easily communicable, especially to stakeholders who need to grasp the effectiveness of our forecasting in straightforward terms. Like you can see in our case, initial MAE was 4.5. In this case, we are saying that there is a 54% error or variation in our calculations, or our method actually. Now, transitioning from MAPE, we now explore the mean squared error, MSE. Another crucial metric in our forecasting toolbox. MSE takes the errors between our forecast and the actual values, squares them, and then averages these squared errors. This approach gives more weight to larger errors, making MSE a critical measure when big mistakes are more costly. Like, especially in an industry, like think about it, I'm going to give you an example. But the scoring aspect of MSE is pivotal. By scoring the errors, we amplify the impact of larger deviations, ensuring they don't go unnoticed. This makes MSE particularly useful in scenarios where avoiding large errors is more important than the smaller ones. For example, in our class in revenue management, an underestimated forecast that leads to a significant loss of potential revenue, right? We know that is a serious concern. If we underestimate forecast, is going to be huge issue from the revenue perspective, even if it doesn't show up much on the error sides. So MSC would highlight such substantial errors more prominently than other measures, underscoring the need for a model that minimizes big mistakes. However, remember that MSC can overemphasize large error due to its scoring function. This means it's most effective when used in conjunction with other measures like MAE and MAPE to get a well-rounded view of models accuracy. I mean, whole point we are trying to make here in the error measures, I'm going to RMSE in a minute also, but don't pick something and it always works. You should be always approach analytically and look at the different options, different error terms. How can you interpret them? That's the whole point of these chapters. Now, after exploring mean squared error MSE, we progress to root mean squared error RMSE, which takes our understanding of forecast accuracy a step further. RMSE is the square root of MSE, bringing the scales of errors back to their original units, making it more interpretable. RMSE preserves the emphasis on a larger errors that MSE provides, but does so in a way that's more intuitive, right? For example, if our forecast errors are significantly off in some periods but not others, RMSE will highlight this variability, showing us the standard deviation of these errors, so we understand what's going on. So essentially, RMSE gives us a measure that is sensitive to large errors, but in a format that's easier to understand and relate to our actual data. It is a powerful tool for identifying when and how our forecasts are deviating significantly, so guiding us toward more accurate and reliable forecasting methods. By the way, I'm going to give example in each of them in the next couple of minutes. So with a range of error measures at our disposal, the next critical step in forecasting is selecting the right method. Now, we have some errors. We understand how to do. We have to use as much as we can, and depending on data, you have to decide which one is the best methods for whatever you're going to do. However, the guiding principle here is accuracy. Whatever method we are using, idea here is trying to be more accurate, right? So we are not just looking for a method that performs well in theory. We need one that delivers in real world conditions. So this process involves testing multiple forecasting methods, applying them to our data, then rigorously comparing their accuracy. We are essentially pitting these methods against each other to see which one emerges as the most reliable and precise. But there is an additional layer to consider: benchmarks. It's essential to ask, is our chosen method more accurate than the simple benchmark? Like we talk about the naive forecast, right? Naive forecast is basically look at whatever the previous previous value was. So the aim is to find a method that not only performs well in isolation, but it also outshines basic, less sophisticated methods. Otherwise, why you want to invest a lot of time in the learning that methods if the naive is handling, right? So it has to be better than naive method at least. So ultimately, the method we select should be the one that consistently provides the most accurate forecast. This decision is critical as it directly influences the quality of our decision making and the success of our strategic initiatives in revenue management. So, is it more accurate than benchmark? Right? What is a good benchmark? I mean, we talk about naive, but you might talk about something else. Is naive an objective measure? Is naive always the appropriate benchmark? Is there a unique patterns? Other simple methods as inexpensive, like maybe you invested in, I'm just making up like machine learning techniques, but you are spending a lot of time. Does it worth it, right? So what's the best alternative? Is the current method. unfortunately, there is no straight answer. There are a lot of trial and errors. You have to, because it depends on data, and different data gives different results. You have to work on your own data. However, the idea behind this chapter is to learn what is out there and what can you use and how you're gonna use it. So lastly, for this session, I'll give you some methods to choose best weights, like for example, for weighted average, or best alpha for exponential smoothing, and best alpha, beta, or gamma, and gamma for Holt Winters methods using the Excel's minimization method. Okay, let's start with our Excel example. Let me get this, copy the formulas first. Okay, these are our formulas, right? So what is the error? Error is basically you take the forecasted one minus the actual one. Okay, let's take this down all the way here. That is the value we have. So that is for regular error term. For the mean absolute error, what we need to do is we need to take this an absolute value of this. Okay, so we are just basically just getting absolute value of the error term. Actually, let's make this 2 digits. Okay. Now, what is the we talk about the mean absolute percentage error, right? So what we need to do is we are going to get here again. Basically, we are getting mean absolute error, right? Dividing the original data, like you can see here, right? Mean absolute error divided the actual one. Let's cover all the way here. And the next one is the MSE. What's the MSE say? You need to get the square of the error term. So you get the error term and square it. Right down here. As you can see, like for example, right, some of the values are extreme, like this is a 438, right? Because error is huge. Actual came 75, you 75.94, and you think it was going to get 55. I mean, it's a huge error in your part. Now, this is good we did so far. What we are going to do is we are going to get to add them so we can get the mean. So we are going to sum up all this. Okay. Then we are going to divide to n, basically how many error terms out there. Yes, we forgot the parentheses as always. Now, just let me show you quickly. We added sum up, like think about here, right? We are doing this part here. We are adding all the errors. Then we are dividing to 1 over n, basically how many n is over there. This is automatically done. Now, let's do the same thing, pull all the way here. Now, of course, this needs to be percentage. Okay. Now, do you remember we talked about that sometime using the mean error is not a good idea because it might lower the error? Look at this here, negative 1.27. So according to the numbers, actually you have a very low error if you look at this one. But when you look at the mean absolute error, you can see is increased to 8. Now, last one is we are going to use the RMSE. What's the RMSE is? You are taking MSE and you are getting the square root of it. Okay. Now these are how the error terms are calculated. Now let's go. Okay, as promised, next step I'm going to show you is how to optimize the values. Like for example, in weighted moving average, we just get 0.5, zero point 0.5, right? Or in exponential smoothing, we got some random number, or Holt Winters, we got some other numbers. How are we going to optimize? How are we going to able to find what is the best values are? So to able to do is the best way. Of course, you can do with the trial and errors, but you don't want to do the hundreds of trials and errors, right? There is a things called in Excel as a solver helps us. Now, first step is always, I mean, I already did it here, but after the forecasting, you calculate the errors, right? What's the errors? You got the forecasted minus the actual. So I already got those values here. The next step is then calculating the RMSE. Actually, let me copy the formula of the RMSE so you can see it here. Now, if you look at the RMSE, what's the RMSE says? You take the square of error. So if you look at here, sum square is basically saying to Excel, I want you to square them all and sum, basically add them all together. That's what this part is over here. Okay, that's what the sum square does in Excel. The next step is the dividing that to n, like how many error terms are. Count A, D11 to D45 is basically says to Excel, count how many cells out there. After that, we take the square root of that value. That's how this works. So how we get the RMSE. Now, how are we going to optimize? Let's go open a solver. Now, there are several steps, actually, not that too hard, but first thing we want to do is, actually, let me delete this so I can show it to you from start. Now, you click on the set objective. What is our objective? Our objective is to get the RMSE to do what? To get the minimum, because we want RMSE to be minimum, right? By changing what? We are going to change this to value. So far, good. Now, if you recall from the weighted moving average, we have a constraint. Basically, when we add weights of t and weight minus t minus 1, it has to be added together to 1. So actually, I created the value here. Basically, it says a sum of this 2. Let's add this to constraint. What we want to do is take this. And what do we want to do? We want that to be equal to 1. Let's say okay. See, everything is done. And you need to be sure that this is clicked. Okay, it's selected. And GRG nonlinear is also selected. When we say solve, let's see. See, values been automatically found. That basically Excel tried maybe, I don't know, hundreds of thousands of different variations and find out these values are the best for us. Okay. Now let's do the same thing for exponential smoothing. Similarly, we calculated error, we did the RMSE, the same steps. But as you can see, there are a lot of difference right now. We'll see what's the best value. Actually, it seems I already did this, but for the sake of for you to learn, I'm gonna delete them all so we can redo it. Okay. Once again, what we want to do, we want the RMSE to be minimum. Doing what? Changing alpha value, because we have only one alpha value. But we have a constraint. What is our constraint? Alpha needs to be equal or greater than 0, or equal or less than 1. So we're gonna do that. Let's do this. Which number? Alpha. What needs to be done? It has to be less than 1. Okay. Or greater than 0. Equal or greater than 0. Let's check and be sure that it needs to be equal or less than 1, greater or equal to 0. So the same thing, we select this one. GRG nonlinear is the selected options. Let's solve. See, it seems the best value for in this case is the 0.63. Okay. Now let's do the same thing for the Holt Winters. I mean, this is also very differs a lot from the actual. This forecast is, as you can see, is not really on the line with what we are doing. But if, as you can see, because of the seasonalities, comes to our forecasted values become closer. But let's find the best value. Okay. You're gonna do the similar approach. In this case, this one is the set objective minimum. Doing what? Once again, let me actually delete this. I want this alpha, beta, and gamma to be minimized. What is the restriction on that? There are two restrictions. Any of this value needs to be less than or equal to 1, or less than, more than or greater than or equal to 0. I already selected this. The same approach again. Click 0 and click OK. See, these are the best values for this. Okay, so this is basically how you optimize different, like a weighted moving average or exponential smoothing or Holt Winters. Okay, thank you for watching.